Quantum physics may force us to rethink what's real. Quantum mechanics has challenged our understanding of the universe in profound ways. One of its most intriguing aspects is the idea that particles can exist in multiple states at once, a concept known as But what happens when we try to understand how these quantum objects interact with each other? This is where the concept of quantum coherence comes in, and it might just change our understanding of reality forever. In this episode, we're going to take a deep dive into quantum coherence, exploring how it works and what it means for our perception of the universe. So, sit tight and get ready for a mind-bending journey. Welcome to our channel, where we explore the most mind-blowing scientific concepts and the latest technological breakthroughs. Join us in uncovering the mysteries of the universe and pushing the boundaries of human knowledge. Don't forget to subscribe so you never miss out on our exciting episodes. Let's start with a quick review of what we mean by superposition. According to quantum mechanics, a particle can be in two places at once, spin up and spin down, or any other combination of properties. We describe this using a mathematical tool called the wave function, which contains all the information about a particle's state. The square of the wave function, S amplitude, gives us the probability of finding the particle in a particular place or state. Now, here is where things get interesting. Quantum mechanics tells us that the wave functions of two interacting particles can become entangled. Entanglement is a unique quantum phenomenon where the particles become correlated, meaning that the state of one particle depends on the state of the other, no matter how far apart they are. This correlation is stronger than any classical correlation we know of. But what does it mean for the particles to be correlated? To understand this, let's consider two particles, each with a spin. If we measure the spin of one particle and find it pointing up, we know instantly that the other particle's spin must be pointing down. That's because the two spins are entangled, and the total spin of the pair must be zero. But here's the twist. Before we measure the spin of either particle, both possibilities, up and down, are equally likely. It is only when we actually measure one of the spins that the other one seems to collapse into a definite state. This is what we mean by quantum entanglement. Now, how do particles manage to be in two states at once while still being correlated? This is where quantum coherence comes into play. Quantum coherence is a term used to describe the relationship between the wave functions of two or more quantum objects. It's a measure of how much the wave functions overlap or interfere with each other. When the wave functions of two particles are highly coherent, it means that they have a strong correlation, and the state of one particle depends strongly on the state of the other. On the other hand, if the wave functions are incoherent, it means that the particles are uncorrelated, and knowing the state of one particle tells us nothing about the state of the other. To see how this works, let's consider two particles with spin. Suppose the spins of the two particles are entangled, and the total spin of the pair is zero. We can represent the spin states of the two particles with two arrows, one pointing up and the other pointing down. If the two arrows are lined up, it means that the two spins are perfectly correlated and the wave functions of the two particles are perfectly coherent. However, if we rotate one of the arrows, say by 90 degrees, the two spins are no longer perfectly correlated and the wave functions of the two particles are no longer perfectly coherent. The degree of coherence between the two particles is now reduced. This reduction in coherence can be quantified using a mathematical measure called the fidelity. The fidelity is a number between 0 and 1. That represents the degree of overlap between two wave functions. A fidelity of 1 means that the wave functions are perfectly coherent, while a fidelity of 0 means that they are completely incoherent. What's fascinating about this is that the degree of coherence between two quantum objects can be used to predict the strength of their correlation. The higher the coherence, the stronger the correlation. This has important implications for understanding quantum mechanics, because it means that quantum correlations can be incredibly strong. In fact, the correlations in quantum mechanics are stronger than any classical correlations we know of. This is why quantum mechanics is often described as spooky action at a distance. But quantum coherence is not just a theoretical curiosity. It has real-world applications as well. For example, in quantum computing, maintaining high levels of quantum coherence is essential for performing computations. The longer the coherence can be maintained, the more accurate and efficient the computation. Similarly, in quantum cryptography, the security of the encryption scheme relies on the properties of quantum mechanics, including quantum coherence. But perhaps the most exciting aspect of quantum coherence is its potential to revolutionize our understanding of the world around us. Recent studies have suggested that quantum coherence may play a key role in a wide range of natural phenomena, from photosynthesis to bird migration. It's even been proposed that quantum coherence may play a role in human consciousness. While these ideas are still controversial, they highlight the importance of quantum coherence in understanding the world around us. Now let's talk about the philosophical implications of quantum coherence. One of the most important questions in philosophy of science is the question of realism. Does the world exist independently of our observations? If we take the Copenhagen interpretation of quantum mechanics seriously, then the answer is no. According to this interpretation, quantum objects only have definite properties when they are measured. Before they are measured, they exist in a state of potentiality. But what if we reject the Copenhagen interpretation? What if we believe that the world exists independently of our observations? In that case, we need to explain how quantum objects can be in two states at once and still be correlated. The answer, it seems, lies in quantum coherence. According to this view, quantum objects are only in two states at once. If they are coherent, if they are incoherent, they must be in only one state. This means that quantum coherence is not just a property of quantum objects, it's a fundamental feature of reality itself. It's a way of bringing about definiteness and objectivity. In this view, quantum coherence is not just a property of quantum objects, it's a fundamental feature of reality itself. It's a way of bringing about definiteness and objectivity. But wait, there is more. Quantum coherence can also tell us something about the nature of time. According to the orthodox view, time is linear and irreversible. The past is gone, the future is yet to come, and the only thing that's real is the present. But what if we took quantum coherence seriously? If we do, we find that time is really a circle. Every moment is connected to every other moment. All moments exist equally. Only our limited perspective gives the illusion of a linear timeline. Finally, quantum coherence can also tell us something about the nature of self. If we are made of quantum objects, then we too must be coherent. Our thoughts, feelings, and actions are the result of the interactions between coherent quantum objects. In this sense, we are not separate from the world. We are an integral part of it. So, there you have it. Quantum coherence is not just a property of quantum objects. It's a fundamental feature of reality itself. It helps us understand the relationship between the observer and the observed, the past, the present, and the future, and ultimately the nature of reality itself. As we continue to explore the mysteries of quantum mechanics, we can be sure that quantum coherence will play a central role. It may force us to rethink what we mean by real, but it also gives us a glimpse of a deeper, more fundamental truth. So, what do you think? Does quantum coherence change your understanding of reality? Let us know in the comments below, and don't forget to subscribe for more thought-provoking content. Thanks for watching.